Let us now discuss about the classification of matter. See, I told you that matter is anything that has definite mass. And occupies some space or volume, right? Matter is made up of particles. What are these particles called? These particles may be atoms or molecules. Okay. Say this matter can be classified into two types. I mean, we can give the physical classification, we can give a chemical classification. Let us see the complete classification of matter. Matter can be divided into physical type and chemical type of matter. See, in the physical classification, I mean, based on the physical state of matter, we have 5 types of matter. Okay. Let me give you those. You all know that matter exists in solids. It also exists in liquid state, right? Of course, in gaseous state also. Then there is something special called plasma state. We'll discuss in detail about all these. And the fifth variety, which is a special kind of thing called Bose-Einstein condensate. This can simply be called Bose condensate. Now, in the chemical classification, we have again 2 varieties. The first one is, there are pure substances. The other one is mixtures. Pure substances are generally homogeneous, whereas mixtures may be homogeneous or heterogeneous. Let us see the classification of pure substances first. In this we have elements and of course compounds. Coming to the mixtures, we got homogeneous and also heterogeneous. Okay. Now within elements, we have different varieties. There are metals. We'll tell you about all these things in detail. It's just a classification or a flow chart that I am giving. We'll discuss in detail about every single thing one by one. Metals, there are non-metals. Of course, metalloids or semi-metals. And finally, there are, of course, noble gases. In fact, noble gases also come under non-metals category, but they are separately mentioned generally because of their peculiar property, special property. Okay, so this is the flow chart which gives you about the classification of matter, physical classification as well as chemical classification. Okay, now let us go for physical classification of matter in detail first. In physical classification, first of all, let us see these three things which we regularly come across: solids, liquids, and gases, right? Let us have some comparison of solids, liquids, and gas. Now, coming to the shape of these three, what do you see? Solids have got definite shape, isn't it? They have definite shape and, of course, definite volume. You can just imagine the crystals. You can just imagine the eyes. Okay. Whereas when you go for liquids, how about liquid? Liquids have, like for example, milk. They have no definite shape, right? They've got no definite shape. Of course, they get the shape of the container in which they are taken, isn't it? If suppose you take them in a glass, they get the shape of the glass. If you take them in a bowl, they get the shape of the bowl, right? They've got no definite shape, get the shape of container. Okay. They have, of course, got definite volume. Yes, they have got definite volume. I mean, volume of a liquid is nothing but the volume that they occupy in a container or in a bowl or in a glass, like that. And coming to gases, what do you see? Gases, we can't see them. Gases have no definite shape, right? And no definite volume also, isn't it? We have so many types of gases. Of course, they're all present in air, with nitrogen being the major constituent, isn't it? Nitrogen is present in air to an extent of about 78%. Oxygen to an extent of almost 21%. The remaining just 1% is the volume of the other gas. Okay. So gases have got no definite shape, no definite volume. They occupy the whole space that is available to them. Right? So that is the basic difference in the shapes of solids, liquids, and gases. Solids have got definite shape and definite volume. Liquids have got no definite shape, but have definite volume. Whereas gases have no definite shape, no definite volume. Okay. Then coming to compressibility. I mean, whether we can compress them or not. The second factor, solids are highly incompressible, isn't it? We cannot compress them that easily. They are incompressible, isn't it? Whereas liquids can be compressed slightly, little bit. I'll tell you why. It is all because of the arrangement of the particles in solids, liquids, and gases. Let me give you that information also. Gases can be compressed readily. See the difference? Solids are highly incompressible. Liquids can be compressed. Gases, of course, liquids can be compressed slightly, whereas gases can be compressed readily. It is all because of the difference in arrangement of particles in them. I hope you know that in solids, if you consider the intermolecular distance in these three types, it actually follows this order. Solids are with the least intermolecular distance. I mean, the distance between molecules is very less. They are much closer when compared to liquids. Now in liquids, the molecules are, of course, little farther when compared to solids, but closer when compared to gases. In gases, gas molecules move randomly in all the directions with a different velocity. And of course, occupy the whole volume that is available to them. So the intermolecular distance in case of gases is much more, isn't it? It is all because of this. The same thing can, of course, be given in the form of intermolecular attraction. See, in solids, the distance is very less. I mean, the molecules are crowded. So the forces of attraction between the molecules of solids, between the particles of the solids, is going to be maximum. So the same thing can be given this way. Attractions between the molecules is maximum in case of solids because the distance between the molecules is much less. Next is liquids. Then finally gases. Right. Now check out the compressibility thing again. In solids, the intermolecular distance is much less. I mean, there is no chance of compressing because they're already crowded. They've already got very less distance or very less gap between them. Lesser gap, how can you compress? You cannot compress the molecule. You can actually compress or you can actually reduce the distance between the molecule. Supposing if in your class, there are say about 15 or 20 students, but suppose if plus 10 students have entered, what all can be done? What your teacher will do? The teacher will try to adjust you people in such a way that the distance between students is less than what it was earlier. It's not that he can compress you people. No, he cannot compress you, isn't it? He cannot compress the molecules. He can only compress or he can only reduce the distance between the molecules. Because in solids, the distance is very less. You cannot compress it. Whereas in gases, the intermolecular distance is maximum. Yes, of course, they've got great distance of separation. Yes, they can, of course, be compressed heavily, right? Because the gap can, of course, be reduced. Okay, so if distance is more, attractions will be less. If distance is less, attractions will be more. So these are, of course, very important. The compressibility, intermolecular distance, and the intermolecular attractions are the most important characteristics. Now coming to flowing capacity or the flowing ability, though not much important, you know that the solids cannot flow, right? Whereas liquids, of course, flow from a higher level to a lower level, right? Whereas gases, as I said, flow in all the directions in a random manner. I mean, gas molecules. In gases, gas molecules move in all the directions with a different velocities. Okay, and they make collisions with each other, of course, with the walls of the container also, right? So these are the basic differences between solids, liquids, and gases. Now let us go for the most important and, of course, the newly discovered states of matter, the fourth one and the fifth one, plasma as well as Bose-Einstein condensation. Now let me tell you what plasma state is. Very interesting. Plasma is something which is formed when a gas is ionized. How do you ionize a gas? When energy is passed into the gas, or energy is given to the atoms present in the gas, of course, the gas is ionized. Then what happens? You get electrons and the positive ion. Okay. When an atom undergoes ionization, you get two species, one consisting of a positive charge, the other, of course, consisting of negative charge, nothing but electrons. So you got positive and the negative things in equal number. Okay. The ions and the electrons exist in case of plasma. Okay. This plasma is of two types. Okay. One is a high temperature plasma. Here the temperature needed for the ionization is much more. Even millions of temperature, millions of degrees temperature is required to get these kind of plasma? Yes, you know, these are generally found in stars. And of course, the fusion reaction, nuclear fusion reaction, which actually occur in sun, okay, found in the stars, of course, found in the fusion reactions which occur in sun. Okay, so there are, of course, things like quasars. Then there are pulsars. These are all found, things which are found in galaxy. Supernovas. Okay, remember these all are the different types of plasma found at very high temperature. Very high in the sense, not just thousands, but in millions of degrees temperature. But at millions of degrees temperature, these are found. And you know the second variety, which is normally found on Earth, is a low temperature plasma. So high temperature, and the second variety is low temperature plasma. Now this low temperature plasma is found in the simple lightning or when something is subjected to combustion, when something is lighted or ignited. Okay, so in lightning, in flames, and of course, in semiconductor manufacturing also, we found this type of plasma. Okay, wherein, you know, the temperature, as I said, here you require millions of degrees. Temperature is needed. Whereas here, you know, a temperature of 100 to 1000 degrees is enough. See the difference? So these are the two different types of plasma that we generally find in nature. You get positive ions and the negative ions, which are equal in number, isn't it? One positive ion and an electron. When an electron is removed, of course, you get a positive ion. This all happens when energy is given to a gas and when it undergoes ionization. Okay, then going for the fifth state of matter. That is the Bose-Einstein condensation. Right. This is again very interesting. You know, it's a superfluid. Is of course a gaseous superfluid phase. It is generally formed at very low temperature. You know, the temperature has to be so low it is formed at very low temperature, like the temperature can even be very near to absolute temperature. Okay. Then what all actually happen when the temperature is about almost 0 Kelvin? You know, the atoms collapse at absolute 0 temperature. Atoms or the molecules, whatever, collapse into a single quantum state. You know, a quantum state can only be understood if you know anything about wave function. It is actually based on quantum mechanics. Single quantum state or single wave function. I'll tell you about this. Of course, not now. All the atoms just collapse into a single form. You just remember this. You know, the temperature has to be very low. I mean, it has to be very low that the atoms are not even moving. Okay, they are not even moving. Now, see, the name of this phenomenon was given because, you know, this phenomenon was first predicted by Satyendranath Bose, an Indian scientist. Of course, the work of Satyendranath Bose was continued by Albert Einstein. Interesting, right? You know, it was actually carried out taking rubidium. Now, this rubidium gas was cooled to about 170 nanokelvin. That is too less. Nanokelvin. This is the temperature where Bose-Einstein condensation was found. I think you all know that there are like things like milli, micro, nano, pico, femto, auto, like that, right? So at 170 nanokelvins, when rubidium gas was cooled, they got a special state of matter called Bose-Einstein condensation. Okay, so this is all about the 5 different states of matter. The first 3, which we regularly come across. Last 2 are, of course, very interesting. Okay. Now coming to the chemical classification of matter. This is going to be very interesting. In fact, simple also. You know, in chemical classification, as I said, matter is divided into pure substances and then mixtures. Let me tell you something about the pure substance. You know, pure substances, as I said earlier also, these are homogeneous. I mean, they consist of as the name itself suggests, they consist of only one kind of particle, one type of particle. Let me tell you that the pure substances are further classified into two types, right? The first one is element and the second one is compound. You know, elements are made up of atoms. Elements consist of only one type of or the same type of atoms. Okay. Coming to compounds, you know, elements combine to form compounds. Elements form compounds. These are all very important. For example, let me tell you that there is a compound water, say hydrogen combines with oxygen to form water. So water is a compound formed when hydrogen and oxygen combine. So elements combine to form compound. Let me just balance this. Okay, now the atoms on both the sides are balanced. You got 4 hydrogen atoms, 2 oxygen atoms. Now these are the elements. And this is a compound, right? So elements combine to form compound. Coming to elements, I mean the characteristics of the elements, as I said, they are made of atoms of the same type. What does it suggest? It suggests.
Sorry, your voice is breaking.
You know, these are homogeneous. Okay. Remember, this is homogeneous. You cannot break an element into still simpler substances. Elements cannot be broken. Next. You know, all elements will have a specific melting and boiling point. Okay. Of course, as I said in the beginning itself, they combine, they react to form compounds. So this is all about elements. And now, as I said, elements undergo certain kind of chemical reactions to form compounds. Okay. Next. Now the interesting part. You know, as I said, elements are made up of atoms, right? Now these elements they are represented in shorthand form using symbols. That's it. Now the interesting part starts. elements are represented in shorthand form. Okay, for example, you all know that hydrogen is represented by a symbol H. Okay, H stands for hydrogen. Now, similarly, there is oxygen, for which the symbol is O, right? You know, the present system of giving symbols to elements was given by Berzelius. Berzelius suggested giving symbols to elements. So, you know, there are certain rules on the basis of which symbols were given. And remember, this is where the periodic table comes into picture. You have to actually have great knowledge of all the elements present in the periodic table. You have to learn all the symbols, elements along with their symbols, atomic numbers, and many more. Now, see, coming to the rules on the basis of which symbols were given. This is going to be interesting. You know, some elements were given symbols on the basis of the first letter of their English name. Like the examples that I have already given. Based on the first letter of their English name. Okay, I can give you some more. Boron. There is a carbon. There is a nitrogen, right? Okay, the first and the foremost important thing that we are discussing is symbols. From this particular topic, you'll get more and more questions. So be a little more cautious. Okay, now coming to the second one. You know, some elements were given taking the first two letters of their English name are the first letter and the letter that has importance in pronunciation. I'll give you example. Very interesting. Either you can go with the first two letters of their English name. For example, helium, for which the symbol is He. Remember, it has to be written this way only. You cannot write this way. This is wrong. You cannot write this way. Even this is also wrong. Right? Then you cannot even go for this. Even this is wrong. A small h and capital E. Even when you write the capital H and small e also, see that they are like this. This is okay. It cannot even be this way also. You don't write it this way. Even this also doesn't look good. So learn properly and follow it properly. See the way I've written helium, and there is something called lithium. Look at this. Then there is beryllium. See this. Okay. Then there is something neon, something called neon. So in all these cases, you can see that the first two letters of their English name are considered, right? H-E-L-I, B-E-N-E. Then how about this? What does this indicate? The first letter, I'm the letter that has importance in pronunciation. In most of the cases, the letter that has importance in pronunciation can be the third letter also. For example, this is going to be interesting. You know, I have magnesium. The symbol for magnesium is Mg. Okay. And there is something called chlorine. Cl. The first and third. Of course, even G is the letter that you are stressing when you are pronouncing this. Magnesium. Magnesium. Okay. So the letter that has importance in pronunciation is G. So it is the third letter. Of course, it has importance in pronunciation. Now coming to that other example, I can give you cadmium. Cadmium. You are stressing the letter D. C and D. D has importance in pronunciation, isn't it? So that way, it can, of course, be the first letter and third letter, first two letters, or the first letter and the letter that has importance in pronunciation. Okay. There is something called palladium. Look at this. You know the symbol of palladium is PD. It's not the first two, not the first and third, but palladium. You are stressing the letter D, which has come into its symbol, right? So this is quite a lot interesting. First two letters, or the first letter and third letter, or the first letter and the second letter is the one that has importance in pronunciation. Got it? Now, the third rule is you know, some elements. In fact, 11 elements were given symbols based on their Latin or Greek names. Very important, very interesting. Based on the Latin names, these are going to be much more interesting. Listen to me carefully. You know, there is a sodium. Here the symbol is not SO, not SD, not SI, not SU, not SM. Something else. You know, guys, it is Na. But why? Because the name sodium has actually come from the name natrium, which is a Latin name. And see, from this they have considered Na. Sodium, natrium. Then there is potassium. K. It's not P or it's not PO. It's not PT, but K. Why? It is because the name potassium has come from the Latin name kalium, from where the letter K is taken. I am going to give you some more now. Try to remember. You know, there is iron. Given the symbol Fe, because it refers to ferrum. Ferrum. Copper. Cu. Cu. is nothing but cuprum. Okay, there is a tin, SN, nothing but stannum. Then lead, PB, nothing but plumbum. Okay. Then, of course, antimony, SB, stibbium. Okay. Then you have mercury. Interesting. Hydrargyrum. Say this. Hydrargyrum. Say we are done with the 8 things. Then we have silver. Ag. You know, it's called argentum. Then gold. Gold is Au. Au stands for arum. Next. Finally, it's tungsten. Tungsten is wolfram. Okay. So these are the 11 elements which were given symbols by considering their Latin names. Very interesting, right? Okay. So there are several other bases taking into consideration on which the elements were given symbols. Okay.